A man is standing so the combined center of mass of him and a wheel axle are directly above the center line of a turntable which can spin around without friction. The man is initially at rest. The man, turntable, and non-spinning wheel axle together have a moment of inertia IMTA about the vertical axis passing through the center rotation of the turntable. The man holds a wheel of moment of inertia I sub W, which is initially spinning in a horizontal plane at the angular frequency I omega sub I. And we're told the moment of inertia of this wheel, I sub W, is 1/4 of the moment of inertia of the combined man turntable axle. And the mass of the wheel is M sub W. And the distance from the center of the turntable to the center of the wheel is D, where M sub W D squared equals I sub W divided by 3. The man, turntable, and wheel axle have a combined man, turntable, and axle. The man flips the spinning wheel over, so it is now spinning horizontally in the other direction at the same distance D it was originally from the center of the turntable. What is the ratio of the, here's the question, what's the angular frequency of the man to the original angular frequency of the wheel, omega sub I? And in what direction does the man now spin? So if you do, here's a top view of it. Here's, we'll start with the side view. Here's the turntable, there's the man, and he's holding this axle part. He's holding one hand above, one hand below. The center of mass of the turntable, the man, combined mass, axle, and the man is right above that. In the center, in the distance to the center of the spinning horizontal wheel is D. And here's the front view of it. You can see that it's spinning this way, so the angular frequency vectorially is up. And here's the top view. So the man turntable initially not spinning. The center of mass of all these non-spinning parts is right above this center axle part of the turntable. He's holding the wheel out, top view. It's spinning around that way. Later he's going to flip it over so that as far as he sees it, the rotation will be the other direction. So pause the video and solve. Here's the answer. The angular frequency of the man in this final state after rotated is 3/8 times the initial angular frequency of the wheel, and it's vectorial upward, which means the man spins counterclockwise as seen from the top view. So the man will be spinning around this way. If you got that answer, great. If you didn't, I will now review how to solve it. Solving the problem now. First, pick a system. Let's pick man, turntable, axle, and wheel, everything. Surroundings, everything else. Then typically draw a free body diagram. So what forces do we have acting on this system? Well, we have gravitational forces, the man, turntable, axle, which we're told all in the center mass of that is right above the center rotation, which is my z-axis. And so I got that force down. I got the force mg of the wheel down. I have some normal force, and those are the forces acting. But those are all kind of acting in the up and down direction. So now pick a coordinate system. So we want to pick a coordinate system that's an inertial coordinate system, which means it's not rotating with the man or the wheel or anything, but it's fixed to the ground. Let's pick a convenient one would be so that it's combined, so that's the center of it is at the center of rotation. For center rotation problems, you pretty much always want to do that. We'll pick X, Y, and Z's coming up out of the board. So we show that on different orientations here. And then you can see all these forces are going to kind of cause moments. Like around this point, this can cause a moment which is going in this would be the Y direction to the board. But we're kind of interested more about in moments and forces and momentum are all vectorial. We're kind of more interested in things spinning around this direction, so that'd be the z direction. So none of these have any vectorial impact on any rotation and spinning from the top view. So after we've done that, we want to kind of, we're going to have rotation. We know we have rotation going on, that's our question. We're going to have rotation, we're worried about rotations of things happening in the z direction. So we'll do angular momentum. We're going to pick a point. If there is a fixed point of rotation that we know about, that's always a convenient point to pick for the point we're going to pick to do momentum about, angular momentum about. We're going to pick a vectorial direction. We're going to worry about things from the top view spinning. So we're going to do a vectorial direction in the z direction coming out of the board. So now let's think about as far as forces, and do I have any net torques around the center of rotation in the z direction? Well, all the forces are acting in and out of the board, so there's nothing that's causing a torque. There's no force acting to spin anything of this system. So we know our net torque around in the z direction around the center of rotation is 0, and so we're going to say the change of momentum around a point, which is the center of rotation in the z direction dt, is this net torque. The net torque is 0, so there's for this value, the change of it is 0, therefore it must be a constant. So now considering the system, this is what we're going to now know. We know angular momentum around the center of rotation of my system, all the parts in my system around the z direction is a constant. That means what it had initially is what it had finally. So we always want to think about directionality. My positive z direction is a counterclockwise spin. Okay, so I'm going to say that. And now what has angular momentum? The turntable angular momentum around the z direction. Well, the man turntable axle system potentially has rotational and translational angular momentum initially around the z-axis, and the wheel initially has potentially rotational and translational initially, and then they'd also both have finals. So this is kind of this equation now we're going to solve, and we're just going to plug in values here. You may want to pause the video and solve it from here if you didn't get to this point, and just see how you do it. Starting to fill in these terms in the z direction. So initially, the rotational, think about the man, the turntable, and this axle, the rotational angular momentum of the z-axis initially of that system. Well, we're told that the man is not rotating at all initially. So omega initially is 0, so that's 0. Translational. So now translational around my center of rotation. So think of all the system condensed down to a point above the center of rotation. And so then it's r cross p of the man system. Well, r is the distance from the center of rotation to the center of the mass of the system, which is 0. And v is 0, so initially this translational is 0 as well. So now rotational of the wheel around the z-axis initially, so that's the moment of inertia times the angular frequency initially of the wheel, and everything always has to be with respect to ground. And it was in this direction, we're told initially from the top view, which is positive, so that's a positive. Translational angular momentum of the center around the center of rotation initially of the wheel, so that's r cross p, and p is mv. Well, I'm told that initially that this is being held in a fixed position. There is no velocity of the center of mass condition initially, so that's 0. So that's all my initial angular momentum around the center of rotation in the positive z direction. Now, after I flipped, so he's flipped it over, and now we're going to start thinking finally what happened. Well, okay, so in the first term is the man disc axle system, which we're told that's still center of mass stays above the center rotation point. Rotational point, we just worry about rotation about its own center of mass. So the center of mass is there. Is the man turntable axle system rotating? Well, potentially he is rotating around there. So let's call that omega is of man final, and omega is always with respect to ground. It's not with respect to the turntable or something else. Omega has to be with respect to our coordinate system, which we pick an inertial coordinate system, which we pick around here. So this is moment of inertia around of the man turntable axle times the angular frequency of the man finally around with respect to ground. Translational is R cross P of, now the man turntable axle subsystem is condensed down to a particle at a center of mass, which also happens to be right on the z-axis, and so the R term is going to be 0, and this whole system's not moving. It doesn't have any velocity around relative to the z direction, so we know that's 0. Now comes the point where probably most of the confusion comes about. So now the angular momentum finally of the wheel about its own center of mass. So we know that's going to be the moment of inertia of the wheel around its center of mass times the angular frequency of the wheel in the final state with respect to ground. Well, what is that? Initially the wheel is spinning this way, and nothing else is turning. So the wheel, his angular frequency with respect to ground is this way. It's the same as the angular frequency with respect to the man, because the man is not turning relative to the ground. But after the flip, how does it work? The man flips it over. According to the man, so let's say the wheel is spinning here at 300 radians per second. And the man immediately flips it over. According to the man, he now sees it spinning 300 radians per second in the clockwise direction. From your point of view, you see it flip, you don't see its speed changing. Its angular frequency changing. But relative to the ground, is the angular frequency changing? So we've just flipped it, and here's the man just flipped it, and now this wheel, and I've drawn directionality because that helps understand. So I kind of put a little point to where the man is, and I point to the wheel that at that moment in time he flipped it. It's now spinning at this instead of the counterclockwise, let's say 300 radians per second, he's spinning clockwise 300 radians per second with respect to the man, as far as the man sees it. But the man he's potentially rotating. So let's draw them both at just a moment later. Now I've drawn this having rotated here, and let's imagine that the wheel's not even spinning for this case. So the wheel's being held by the man and is pointed this direction. If there was a mark on the wheel or something, or a point on it, so there's some little mark, and we just watch that mark. So let's pretend the wheel's not spinning, but the man's holding it and he's rotating. So it's pointed this way, and then as the man's holding and he rotates here, it stays the distance d away from the center of rotation, but this point is now pointed in a different direction. So the wheel has a rotational about its own center of mass because it's part of this other system that's rotating. And now, so you can view that. So that's one part of its rotation. Another part of its rotation is how it's rotating relative to the man itself. So rotations, velocities, displacements, everything is relative to something. You have to say what it is. Normally we just put a velocity, and you say, well, that velocity is with respect to my coordinate system. If you're driving your car and you're saying going 70 miles an hour, you don't normally say 70 miles an hour is relative to the ground. Everybody assumes, yes, I'm relative to an inertial coordinate system, which will assume the ground is in this case, and I'm moving 70 miles an hour relative to that. Or if I have an angular frequency of so many radians per second, if you don't mention it, normally you think, well, that's relative then to my inertial coordinate system, which is ground. But in some cases, we have to really think about relative to what. And so let's think about even velocity. For example, let's say the ground is a coordinate system, and this one part's moving here at this velocity magnitude, part A with respect to ground, and part B is not quite moving as fast in this x direction. It's going a little bit slower with respect to ground. well, what's the velocity of A with respect to B? If you're standing on B, you see A slowly moving away from you. And so one way to think about here is the velocity of A with respect to B is the velocity of A with respect to ground minus B with respect to ground. So that's that equation right here, which is valid. Another way to think about it is if I take this term over here and I bring it to this side, well then I'll have, so this term, I'll move it over here, velocity of A with respect to ground equals the velocity of B, A with respect to B, plus now the velocity of B with respect to G. And this is a way I like to think about it because with in these little dashes, these little slashes here is one way to shorthand them as saying A with respect to ground, or A with respect to B, or B with respect to G. And when you write it this way, it's easy to remember because I can see that the denominator here is the numerator here, so they kind of match up, and that's easy for me to think about that. Okay, so the same thing happens for angular frequency. So we're thinking for conservation of angular momentum, it's angular momentum about a point in a direction relative to an inertial coordinate system. And that inertial coordinate system, in this case, is the ground. So this is what the term that belongs in here. When I'm talking about rotation, anytime I'm talking about rotation with respect to inertial coordinate system, it's not rotation with respect to, it's not the wheel with respect to the man, it's the wheel with respect to the ground. So we want the wheel with respect to ground. Well, we know right here, so that's the wheel with respect to the man plus the man with respect to the ground. And we were told here that, so we know when he flips it, we know that the magnitude of this media is going to stay constant. As far as the man sees it, that magnitude of the angular momentum used to be in this direction, now it's in this direction. So with respect to the man, with respect to man, it's going this way from the top view at the same amplitude that it was initially. Nothing changed. Well, then I need to get this term. I need to think, what's the man with respect to the ground? Well, the man with respect to ground, that's this. Which I said in my final, with respect to ground. So you can see that these are gonna, they're not in the same direction. This one's in the clockwise, so in the minus C direction. This one's counterclockwise in the plus C direction. So this is going to be we call this the positive Z direction is out. We're doing everything positively here. So in the end, so this is going to be a positive term, this is going to be a minus term. So what goes in here is the omega m sub f with respect to ground. And then this is in the minus this w sub I with respect to ground. So we can write it as the dash g if you want to, but it's really the same term as that. So that's kind of the confusing part. This frequency, everything has to be velocities, everything has to be with respect to ground. Thinking about the translational angular momentum of around the center rotation of the wheel in the final state. So that's r cross p, where r is going from this point to there. So that's my r vector. Center rotation to this. The wheel is now considered to be condensed down to a particle at center mass. And so that's r. P is gamma mv. Assume gamma is 1. So mass the wheel. Well, what's the velocity of the wheel with respect to ground? Well, we're told the velocity of the wheel is the wheel is being held by the man, and so that velocity of the wheel is in this direction, and he's this distance d from the center, and he's at this angular frequency is what this man's holding the center of the wheel, now condensed down. So the velocity is r times omega. This is r is d. the frequency, angular frequency is the omega of the wheel. Not the omega of the man, not the omega of the wheel, but he's going with that. He's going with the wheel. So he's going with the man is holding the center of the wheel, and so the velocity is not depending on the spinning of the wheel, but depending on the velocity that the man is rotating. Okay, so the mass of the wheel times d. The velocity is d times the angular frequency that the center of mass is going. So r cross that. R is in this direction, going from this point to here. Velocity is here, so that's going to be a positive term. You can think about a particle spinning around the center is going to be in the positive z direction. And so ultimately, it's going to be this term will be, for as far as r cross, the magnitude of r cross p would be mv, and I already have d there. R would be another d, so d squared times the mass. So this is what that term becomes: the mass times d squared, because I have r here and another r here, which is d, times this. So that's what this term is, and this we said it was positive. So now we've defined all these terms. We just need to do some algebra and simplify it. So on this term, and I dropped the subscripts with respect to ground because everything now we said with respect to ground, just to make it a little less lettering on the board. But we have I omega initial on this side. Now we have some terms. We have this term, and this term now, which have omega final of the man. So combining all those together, we were told from here that the moment inertia of the wheel is 1/4 the moment inertia of the man. So therefore, the moment inertia of the man entire turntable and axle is 4 times this. So I can replace 4 moment inertia with that. It's the same magnitude, and then times this. This is plus 1 of these, and then I have this term right here, which is my mass of the wheel d squared from here. So I've now captured this term and this term, and I got this one. I didn't capture this one, which is my minus I omega, the I of the wheel times the initial angular frequency of the wheel. So now this is my entire thing. I can bring this over to here to get 2 of them, and then divide it by this quantity to solve for the omega final of the man. So this is what and then also, so these two combined here become 5. I was told up here that my distance is such that the mass of the wheel times d squared equals 1/3 of moment inertia of the wheel. So I can replace this with 1/3. So this is 50, and you can see that each term has I omega. You can cross those out. So got 2 here. 5 is this. I can solve for this, and in just simple algebra, I end up that the final angular frequency of the man is 3/8 the initial frequency, angular frequency of the wheel, and it's positive, which means that my assumption was right, that this whole system is spinning in this counterclockwise direction. And thinking about it from the top view, the final case, the angular frequency of the wheel with respect to the man is this omega sub I. We found out that the whole system, the man, turntable, axle, and center of mass of the wheel is spinning at 3/8 omega sub I this way. And so the final, if you took snapshots of the wheel, and you see that the wheel with respect to ground is spinning in this direction 5/8 of omega sub I.